Solids by known cross-section, example 3. This problem comes to us from the 2007 AP Calculus exam. It's a little bit unusual in that we were not given a diagram from which to work. Let R be the region in the first and second quadrants bounded above by the graph of y equals 20 over the quantity 1 plus x squared, and below by the horizontal line y equals 2. I'm not interested in parts A and B here. I'm only interested in part C for this lesson. The region R is the base of a solid. For this solid, the cross-sections perpendicular to the x-axis are semicircles. Find the volume of the solid. Note that there are two functions mentioned here. Before we proceed, please pause the video and put the two functions into your calculator and adjust the window so that you can see the region between the curves. Okay, so this is what the graph should look like. Here is the region referred to as R. We are slicing perpendicular to the x-axis for this problem, so we sketch a representative slice and try to give it the feel of a semicircle coming up off the page. When I make such sketches, I try to give the impression that there is a three-dimensional view. One technique that you will find helpful is to give unnamed functions a name. You do so with a let statement, which you write as part of your solution. That way, you can refer to the function by the name you gave instead of by writing out the function every time you want to reference it. The distance between these curves is f of x minus 2. But we are going to need the radius. So we will divide that distance, really the diameter of the semicircle, by 2. The area of a semicircle is 1/2 pi times the radius squared. Substituting our found radius, we get this expression, and we're careful about the grouping symbols here. The 1/2 squared times the other 1/2 from the area formula give us 1/8. Don't forget about pi. When we multiply this area formula by the thickness of our slice, dx, we get an expression for the volume of the slab. Recall that the volume of the slab is just a small portion of the volume of the larger object whose volume we are trying to determine. Before we integrate, it will be helpful to consider how far to the left and right we can make such semicircular slabs. It should be clear that we can do so between -3 and 3. So those numbers become our limits of integration. Plug that integral into your calculator to verify that you get the same result as reported here. 174.268. Let's take a quick look at the object whose volume we were computing. We showed a representative slice, but really the figure is made up of an infinite number of slices. And the result is this curious object.